Hello. This is a very important video for me. I've been wanting to do this for a long time, so I hope you find it very interesting. In this video, we are going to look at solving two-dimensional finite difference equations. I will show examples of solving 2D linear equations, but as you will see, the iterative methods from my previous video are also incredibly easy to apply to the 2D finite difference equations. So if you've seen my previous videos, I have stated that the finite difference method is used to solve ODEs and PDEs. It requires discretizing the domain into discrete pieces with finite difference, such that derivatives become finite difference equations, and thus the finite difference method is a numerical method. So let's go back to our 1D case and start using index notation. Here, the indices go from 0 to n, where n is the number of points that we split our grid into. Our finite difference equation then becomes the function evaluated at the grid points. The equations to solve are still the same, all we've done is remove any reference to the actual value of x. So what about 2D? Let's remove the solutions for now, and reduce the grid size for clarity. And let's go ahead and draw a 2D grid. So here we have a 5x5 grid. A grid is essentially a uniformly spaced set of points on which we evaluate our solution. Each point is uniquely indexed in both the x and y direction, with x being the columns and y being the rows, starting from the bottom left. By linking the grid, we can derive finite difference expressions for a 2D partial differential equation. So consider a point. Here we've chosen the point x2, y2. We can use index notation n and m for the x and y positions, so this point could be any generic point. We see that we have a relationship between grid points spaced apart, so let's derive some expressions. We know that the second derivative can be approximated as this, using the central difference approximation. I've shown this in 2 of my previous videos. Now that we have a 2D grid, we can also derive an approximation for the second derivative in the y direction. So here, remember that n references the x index and m references the y index. We can see that it's the same equation, but with m instead of n, so these equations are basically the same, but with a different index in them. Combining these two indices, we can find the 2D expression for the 2D finite difference approximation. So here you see we now have a dual index of both an n and an m term. The finite difference approximation for the second derivative for a uniform 2D grid. The nodes at which we evaluate the function is called a stencil. The stencil is often drawn as just the points to evaluate. In this case, the point to evaluate and its 2 closest neighbours along both independent axes. From this extension of the 1D finite difference to the 2D finite difference, it is simple to derive the different derivatives of higher orders. So for example, extending to 3D, you would have 3 equations in which you've introduced a third index, k. The corresponding stencil for this would look something like this. It's a 3-dimensional stencil. Note how the h squared remains in all of these equations regardless of the dimensions in which we are evaluating the functions. Because remember, the h squared is to do with the order of the approximation, not the order of the differential or spatial terms. So let's use these approximations to solve the following equation. For now, we will leave the boundary conditions out. So the first thing to do is to make the finite difference approximation for each independent axis using the equations we've just derived. We then substitute into the equation we are solving and rearrange and collect the terms. This equation is now ready to be solved. Now for the 1-dimensional finite difference, we created a 2D matrix. For the 2-dimensional finite difference, we could create a 3D matrix and attempt to solve it. However, computers are really good at solving 2D matrix equations, and even better at solving sparse matrices. Is there a way to transform these equations though so that we solve a 2D problem? instead of a 3D problem. So let's go back to our grid, and what we're going to do now is we're going to unravel the indices. And all that means is that we've concatenated the rows of the matrices together to form a long row vector. So you can see here how each row is concatenated to the previous row. We then go ahead and relabel the indices 0 to n squared, which for our 5x5 grid is 0 to 25. We can then see that we have a single vector of length n squared. All we need to do now is find the transformation for our grid-based finite difference equations. And we'll go ahead and replace the n, m, so our dual index, with a single index, which will be given by the equation n plus nm. This gives us what we need to solve the equations, an unravelled index. Re-inputting our matrices into the previously derived equation, we are left with an expression relating the value of the function f to its unravelled index. And if you've seen my previous videos, we know how to solve this equation. Before we fill our matrix, we will make a small substitution so the matrix looks a little bit nicer by replacing the expression in the parentheses with the function g. This system of equations can be expressed as an n squared by n squared matrix, that is to say a 25 by 25 matrix for our 5 by 5 grid. So this matrix is a little too hard to visualize on this YouTube video, so instead what I will do is I will highlight the cells as a non-zero. We can see the familiar symmetry as we had in the one-dimensional case, but this time with another diagonal strip offset to the left and right of it. These additional diagonals are one column away in the 2D grid from the main diagonal, and are thus the m+1 and m-1 terms. We must notice, however, that we are missing 16 of the rows out of the matrix. Thus, the matrix system is unsolvable as it currently stands. So what are we missing? Going back to the grid, if we look at the boundary to the grid, we see that there are 16 points along the edge of this 5x5 grid. Quite often we will be given a differential equation to solve and the boundary conditions. Physically, this is also quite often the case, as we usually know the conditions at the boundary, such as thermal insulation in the heat equation, or load or zero displacement in structural mechanics. So back to our equation matrix, we can see that x equals -1 corresponds to the 0 index and x equals 1 corresponds to our big N index. Likewise, y equals -1 corresponds to our 0 index and y equals 1 corresponds to our big M index, which gives us a relationship between the actual values of x and y and the indices to which we have derived on our uniformly spaced grid. We can now fill in the boundary conditions to our matrix. We can see that the boundary points for the solution f to a particular value and the node on the inside of the boundary are evaluating using their neighbouring points. There are only 9 rows in this matrix that are not fixed. That is, there are 9 points to which need to be calculated. These are the inner points contained within the boundary. As the number of nodes increases, the ratio of unknown to known points increases. So for example, a 10 by 10 grid has more points in which are unknown on the inside of the boundary than compared to our 5 by 5 grid, which has less points to be calculated than are known by the boundary. And so just to finish this equation, we can write the right hand side of it. Now I do have to say here that showing a 25 by 25 matrix and a 25 row column vector is quite impractical, but I wanted to show you the raw process. I think it's very nice to see how our original 2D grid problem becomes a 1D vector problem that is solved by a matrix equation. It's also very good to see the symmetry of the matrix along the diagonal, along with the sheer amount of zeros in the matrix. Such matrices can be stored in memory as a sparse matrix, which reduces their complexity from n to the 4 to n squared for a 2D grid, and from n to the 6 to n cubed for a 3D grid. Then, sparse matrix solvers such as mumps, paradiso and spools, for example, can be used to solve these directly, That is to say, we'll get the exact solution at the grid points. So what I'm going to do now is I'm going to show you the solution to this problem for various grid sizes. So here we can see the matrix for a 5x5 grid, but I will show a video in which I solve it on much larger grids too. And for anyone who's not seen my previous videos, the solution to this can be found by recognizing that this equation is a matrix equation of the form A multiplied by F equals B, where A is our simultaneous equation matrix, B is our equation solution vector, and F is our actual solution vector. Then by inverting A and pre-multiplying both sides, we can get the answer to our solution vector F. So back to the equation at hand, along with the boundary conditions, we're going to set alpha equals to 0.15 and beta equals 0.66. And if anyone's wondering, the analytical solution to this equation is given by this. Now, the moment the video has all been leading up to, our solution. As I play the video, the plot on the right is the finite difference solution using the method that we just went through, and the plot on the left is the analytical solution. What I will do is I will show the finite difference approximation for different sizes of grid. So I'll replay the video again. We can see that with two little grid points, the solution is wildly inaccurate, which kind of makes sense as the exponential function is an infinite sum of powers of x and y. And so two little points spaced far away, and we can't approximate the higher order derivatives well enough to correctly estimate the curvature of the equation. As the grid points increases, the approximation becomes better and better, as you can see here. Computationally, the accuracy of our solution needs either more grid points or higher order approximation. The more grid points requires more RAM and more computation time to perform the inversion. Likewise, a higher order approximation needs more matrix elements and hence RAM, and also more computational time. In general, higher order approximations are more efficient memory-wise, but computationally a large grid may be more efficient. So let's do another example. Let's try and solve this equation instead, with the boundary conditions given by this. And let's set alpha equals to 1.5 times pi and beta equals to 2.5 times pi. And again, for anyone interested, the analytical solution to this is the multiplication between sine alpha x and sine beta y. And what I'll do is I'll solve this equation for different grid spacings h on the right and compare it against the analytical solution on the left. And again, we can see some wild behaviour at first, with the solution eventually taking shape as the number of grid points increases. So the smaller the grid spacing, or the higher the number of grid points, the more accurate the solution becomes. Now here's an interesting problem. What happens instead if we let alpha and beta be even multiples of pi? In this case, our boundaries would be 0 according to this equation. And we can quite happily put in these 0 boundaries into our finite difference approximation, and our solution would look like this. What? The solution is 0. And there's nothing wrong with this. 0 is a perfectly valid solution to our differential equation. You see here, having f equals 0 everywhere does indeed satisfy our differential equation. In this case, the boundary of 0 leads to a 0 solution. The boundaries are not enough to uniquely generate the surface. So, we have a problem. And this is because the boundary conditions that I've used in this video and previous videos have all been Dirichlet boundary conditions. That is to say, we specify the value of the edges for 1D, the values for the circumference in 2D, and the values on the surface in 3D. So we actually give the value of the function itself. There is another type of boundary, however, called a Neumann boundary condition, where the gradient normal to the boundary is specified. These types of boundaries require a bit more thought that I will explore in a later video. But a Neumann boundary would have worked for the previous example, since the gradient along the edge is non-zero even though the solution is. So thanks for taking the time to watch this video. As I've said, I've been waiting a long time to do this, and I hope it helps some of you watching. In the next video, we'll take a look at what we've learned and apply the finite difference method to solve some actual physical equations, such as the steady-state heat equation. We will include problems with both Neumann boundaries as well as Dirichlet boundaries, and we will see how such boundary conditions are actually natural in such problems and how we can apply the finite difference method to solve them. So stay tuned.